All right, let's try to solve this problem using dimensional analysis. Okay, the first thing I'm always going to do with dimensional analysis is write down all of my variables that are given and my units, and then write down what I'm solving for. So the first thing in this is that it's a 250 milliliter flask. So I'm going to go with 250 milliliters. Okay, it's contained 0.423 grams of vapor, so 0.423 grams. And I'm going to put the units on it and make sure that I include those on there. It's at 100 degrees Celsius, which I'm just going to do in my head is 373 Kelvin, 373 Kelvin. And then it's at 746 torr. Now, I've got the ideal gas constant memorized for atmospheres, so I'm going to convert this into atmospheres knowing that there's a 760 conversion rate. So it's whatever 746 divided by 760, and this is in atmospheres. Now, I could actually do that math, and it could be slightly less than 1 because it's smaller than 1 atmosphere, but we'll see how that goes. All right, once I've got that, then I can simply, the question is asking, what's the molecular weight of the compound? Molecular weight is going to be in equals to grams per mole. Those are the units I know I'm looking for, so that's going to be my answer. So I'm looking for grams in the numerator, moles in the denominator, and let me look through here, grams. So I know for a fact that's going to be 0.423 grams in the numerator, and I don't care what's below it, right? It's just there, it's a constant. Then I'm looking for moles, I don't see it, so what I can do is I can say, well, in that case, I'm going to use the gas law constant, 0.08206 liters atmospheres per mole Kelvin, liters atmospheres on the top, mole Kelvin on the bottom. That's where I need my moles. So I'm going to say 0.08206 liters atmospheres per mole Kelvin. Now this is per 1 mole Kelvin, but really it doesn't really matter because that's where my units are. So I've got moles in the denominator, moles in the denominator, that's great. But I now need to cancel out liters, atmospheres, and Kelvin. And I've got a bunch of those there, so I know I'm on the right track. Let me start with the Kelvin, 373 Kelvin. Kelvin's the denominator here. So it must be in the numerator here, 373 Kelvin. I've got atmospheres in the top, so I must have atmospheres on the bottom. So 746 over 760 atmospheres, right? And then I can invert that if I really want to be pretty with my math. And then what I've got is liters. So I know that I have milliliters, but I need liters. So I'm going to say I put liters down here where I know it's going to cancel out. I've got milliliters up here. And there are a lot of small things for one big thing. Milliliters are small, liters are big, so it's 1,000 milliliters per 1 liter. At that point, I've got milliliters that I need to cancel out is going to be 250 milliliters. So at this point, I've got milliliters canceling out with milliliters, liters canceling out with liters, atmospheres canceling out with atmospheres, top and bottom, top and bottom, top and bottom, Kelvin cancels with Kelvin. The only units I'm left with are grams and moles. So if I do 1 times 1,000 times 1 times 373 times 0.8206 times 0.423 divided by 250 divided by 1 divided by 746 divided by 760, that should equal my answer. I will leave that as a exercise for the viewer.